Okay, so continuing with our discussion about common nucleophiles and electrophiles. So a very common electrophile would be what are considered, they're commonly considered alkyl halides, although in the IB curriculum they're either called haloalkanes or halogenoalkanes. I think actually the halogenoalkanes is the most common term, but I would argue that more commonly they're referred to by one of these two names right here. So what makes them electrophilic is that you've got a carbon which is connected to either a bromine, chlorine, or an iodine, and the electronegativities of these are greater than the electronegativity of the carbon next to it, and that makes that carbon right there slightly positive. All right. Another common two other common electrophiles are either aldehydes or ketones, all right? And their electrophilicity comes from the fact that oxygen is more electronegative than the carbon that it's bound to, which pulls these electrons towards the oxygen, which creates a slight positive charge or a delta positive on that carbon right there, all right? So technically something that would qualify as an electrophile would be your typical Lewis acids. A boron that's got 3 groups attached to it. You also could have like aluminum with 3 groups attached to it. This is not, even though these would definitely act as electrophiles, you wouldn't see them as electrophiles in reactions that much because they tend the only thing that really can happen is a nucleophile, a lone pair can bond to them, all right? And it's not like a further reaction would occur after that. All right. One electrophile that we're going to be talking about in a little bit is this electrophile right here. All right. This chemical species right here is called a nitronium ion. All right. You can see that it's got a central nitrogen and it's double bound to 2 oxygens, and that puts a positive charge on on the nitrogen atom. All right. It could also be represented with this formula right here. So one thing that I want to point out about this is this particular species, even though it's very important for organic, a certain type of organic reaction, it has to be created in a reaction in order to be used. All right, and the way that you say that is that it's created in situ. All right, this is a Latin term right here. in situ, all right? And whenever in chemistry you say something is created in situ, that basically means it's created on the spot, all right? It's created in a reaction, all right? Because it does not exist in a stable form in a compound, all right? So for example, obviously you can take a look at this and see that it's got a positive charge, all right? You might think, well, this could act like a positive ion, and we should be able to have nitronium chloride or nitronium bromide, all right? This would not be stable as the cation of an ionic compound, all right? The way this typically is made is you take nitric acid, which is NO3 plus, and you stir that in pure sulfuric acid. And when you stir those two chemicals together, some of this gets made, all right? So yes, it's very useful, but again, you have to make it in a reaction in order to use it, all right? So again, here, in situ just means it's created in a reaction, but it can't be isolated, all right? So a very classic reaction that involves an electrophile being attacked by a nucleophile is what's called a substitution reaction of halogenoalkanes. Okay, and again, a lot of times these types of compounds are just referred to as alkyl halides. All right, so the interesting thing about this reaction is that it can occur through two slightly different reaction mechanisms. Okay, the first of these reaction mechanisms is what's called an SN2 displacement or an SN2 substitution. All right, notice that when you write that, it's all the letters are capitalized, but the N tends to be subscripted like that. All right, so what makes an SN2 substitution and SN2 substitution is the way that these things react. All right. So the way I've drawn this right here, I've drawn it on purpose, where you can see you've got a hydrogen right here going back, you've got this hydrogen coming forward, but you've got this methyl group coming forward, and this bromine would be going straight to the right. All right. And so when an SN2, excuse me, when an SN2 substitution occurs, it occurs with what's considered inversion of the stereochemistry. All right. So what that means, the best way to describe this is to think about what happens when an umbrella gets inverted in a strong wind. All right. So here we have a picture of essentially an umbrella that's been caught in a strong wind. All right. And one thing that you probably realized about this is that, I mean, the normal function for this is for these little ribs right here to be going towards the left. All right. But what happens in a strong wind is essentially the things that were going to the left are now going to the right. All right. So think about this area right here as being a carbon atom. All right. And let's pretend that we start off with this umbrella the way it normally would function, with these metal ribs coming towards the left. All right. And if you had that, essentially that's what these bonds right here would represent. All right. You've got your central carbon. All right, so these bonds would be like the ribs of the umbrella going towards the left. All right, and what happens is the electron pair is going to attack that carbon, and when that happens, when this reaction happens, the ribs that were going towards the left are now going to be going towards the right, shown like this. All right, so it's essentially like, you could think of it like a wind was coming from the left here, blowing towards the right. In this umbrella, the ribs get kind of inverted so that they're now going the other way. All right. So the way this mechanism works, with the mechanism, first the nucleophile is going to attack the carbon. All right. And instead of these bonds being immediately being converted to the opposite, you originally go through this intermediate step. And what this shows right here is that there's a bond that's starting to get formed between the oxygen and the hydrogen. And you've got this bond right here, which is starting to depart. All right. And in this, one thing about this particular intermediate right here is that these bonds right here, this, and this, would have a trigonal planar arrangement if we just looked at that right there. All right, so a way that you can think about it is like, this is kind of like an upside down Y. All right, where this is I guess normally the stem of the Y, and here's the two things that normally make up the top of the Y, and we're kind of looking at it on its side. All right, and as this progresses, you're going to get, this bond is going to completely form, whereas this bond is eventually going to get broken. And when that happens, notice you get inversion of that stereochemistry. All right, these bonds that were kind of going to the left-hand side are now going to the right-hand side. All right. So the reason that this is called an SN2 reaction is that overall it's going to be a second order reaction. All right. So if you think about how this reaction proceeds, it would involve the collision between this hydroxide right here and the alkyl halide. All right. So it involves two things being able to react. All right, as the rate limiting step. All right. And if you remember back to kinetics, all right, if you have two things that need to collide in the slowest, which is the rate limiting step, then those things would both be in the rate equation. All right. And so since there's two species in the rate limiting step, that one way of saying that is that it's bimolecular, or that it has a molecularity of 2. All right. I would commonly just say that it's a second order reaction. All right. So that the 2 in the SN2 comes from the fact that it's a second order reaction. All right. But when you're talking about, so again, even though the 2 in SN2 is there because it refers to the fact that it's a second order reaction. Generally, what people are going to think of when they think SN2 is the fact that the stereochemistry gets inverted. All right, and that'll make a little bit more sense, hopefully, when we compare that to an SN1 reaction. All right, so the difference between an SN1 reaction, so one of the things about an SN2 reaction is that you only get one product. All right, let's pretend that instead of this right here being a hydrogen, all right, let's pretend that it was some other group. All right, well, the thing is, in order for this reaction to occur, there's only one direction for this leaving group to leave. It's got to leave from the right side. All right, so that makes only one product. All right, but as you're going to see here, when you have an SN1 reaction, you can get more than one product. All right, so so again, you're going to eventually we're going to get a bond between this oxygen and this carbon, and this bromine is going to leave. The difference is that they don't happen in the same order as before. All right, so let's pretend that this happened with the inversion of these groups, just like we did in the SN2. All right, so think of the umbrella as going towards the left. All right, and let's pretend what would happen if you made a bond here and things are then bent to the right. All right, that would end up making this product right here. All right, so and if this were to happen by an SN2 reaction, excuse me, this would be the only product that you would form. All right, but the thing is, when you do this reaction right here, you actually not only get this product right here, you also get this product right here. All right, and notice that the way that these bonds right here are arranged, it's exactly the same as the way that the bonds were in the starting material. All right, so notice you actually get two products right here. These would be enantiomers of each other because they are mirror images of each other. All right, so the reason that we get the two separate products here is because of the mechanism of how this works. All right, so as compared to before, we first needed to have the hydroxide come in and attack the carbon. Well, here we're going to get a step that doesn't involve the hydroxide. These electrons in this bond are going to go onto the bromine. All right, and so this essentially we're going to have bromide leave the molecule. All right, and once that leaves, that's going to leave this species right here. All right, so again, this species right here is very much like this, what you saw in the center right here. All right, again, you can kind of think of it as a letter Y that you've turned upside down and you've twisted the top so that the two things are kind of one right in front of the other. All right, obviously I've got to draw it a little bit from the side so that you can see that there's two groups down here. But if I turn this, it would make a complete letter Y, or upside down letter Y. All right, so this thing is what you call a tertiary carbocation. All right, the tertiary comes from the fact that bonded to this carbon right here are three different carbons. All right, that's a methyl group, an ethyl group, and a propyl group. So each bond would be to a carbon. All right, and the thing is, this is relatively stable. All right, tertiary carbocations and secondary carbocations are actually stable enough that they can exist in a solution. All right, for the most part, primary carbocations don't really exist. All right, they're very unstable. All right, so because this thing right here, one reason it's necessary for this to be stable is this reaction right here would not have occurred if this was not going to make either a secondary or a tertiary carbocation. So, for example, if both of these were hydrogens instead of the groups that they are, the group that got made would only be a primary carbocation, and those are not stable. All right, so if these two things were hydrogens right here instead of alkyl groups, this right here would not exist. All right, because primary carbocations are not very stable. All right, so this thing right here can stick around for a decent amount of time, and so this is going to act as an electrophile. All right, so what can happen is that the attack can happen from either the left or the right side, and that's why we get the two different stereochemistries.